Okay, sorry, I was not aware that.
We give you a lot of responsibilities here. Okay, super. So thank you all for coming. This is the second of two talks from Francesco Petruccione. We're really delighted to have you here. Thank you so much for coming. We went through this last time, but it's always worth going through again. So Francesco is professor of University, interim director of the Francesco was previously professor and total vice chancellor of informatics. Hopefully we still have. Yeah, geez. Yeah. Hopefully this room is super. Yeah. So really delighted to have you here. I think the two talks on.
There's noise coming from, I'm not sure. Anyway, so last time I was here a few weeks ago, I gave you, I don't know if all of you were here at the time, but some of you were, a rough overview of quantum computing. And I think I might have spent too much time in trying to reduce the hype. So that's why probably there are a few persons in the audience today. So there was a strategic mistake. Yeah. And and among the things that I said was that probably quantum machine learning is probably the last one of the applications that will make sense. Yeah, but nevertheless, it's a fun thing to do. Yeah. So what I will do this morning or this afternoon, I will start very generic with the idea of quantum machine learning, maybe reusing a few slides from last time just to get into the mood. Then I have a little parenthesis on the Deutsch algorithm, mainly because you ask about oracles. I give you the oracle. I give you your oracle, yeah. Then I will explain what is probably the analog to the Deutsch algorithm for machine learning, which is a very simple Hadamard classifier that just one Hadamard gate and it classifies them, that we developed in the meantime long ago. Then I will give you a non-technical overview of variational circuits applied to machine learning problems. Yeah? And I will finish with something that we just published a few weeks ago, yeah? on convolutional neural networks, the quantum version. Yeah? So let's start with the idea of quantum machine learning. Obviously, as the name says, it's the intersection of machine learning and quantum computing. Yeah, no big mysteries there. Yeah, but what is maybe more interesting is that it's not such an old discipline, yeah, in the timeline of quantum computing, yeah? Because if you can say that the serious birth of quantum computing was 1994, yeah, which is almost 30 years ago, yeah, with the famous algorithm by Shor, it only started roughly 10 years ago, yeah, mainly after people found like Seth Lloyd and company found out that you could solve linear systems of equations with quantum computing. That essentially you can do linear algebra, yeah? Which is not surprising because quantum mechanics is essentially linear algebra. Yeah, yeah? So it's a fairly modern development, and this is a cut and paste from some old publication. But the curve shouldn't go asymptotic. I think it's on the exponential side. Yeah? Still growing. Yeah. In classical machine learning or normal machine learning, you can roughly divide in three categories: yeah? Supervised, unsupervised, and reinforcement learning. Yeah? Supervised learning, typical application of the pattern recognition. Unsupervised learning, data clustering, and the usual games and things like that for reinforcement learning. Yeah? And the idea is, of course, try to generalize it, do it quantum. Yeah? So how do you do it? Yeah. Essentially, there are rough, and this is also, you see, almost 10 years ago, and that we wrote this first review article about these things. There are some kinds of classical machine learning algorithms. Now, I assume that maybe you know a minimum of machine learning, yeah? Or k-nearest neighbor, support vector machine, and so on and so forth, that are based on computing distances to some hypersurface or to something, yeah? And that's fairly obvious how to do it quantum, because quantum computers can do nicely scalar product. And those are essentially distances, yeah? So there is hope to do that, yeah, fairly obvious, yeah? Neural networks, decision trees, in this original 10 years ago, we said first exploration, yeah? The challenge is that, neural networks are intrinsically nonlinear. Yeah, and quantum mechanics is famous. Yeah, so there is a problem that needs to be solved. Yeah, and now there is something that we call quantum neural networks, but it doesn't really look like a neural network. Yeah, but anyway, I will show you to you just now. Yeah, and then there are these more, let's say, more stochastic approaches based on Bayesian probability theory, Markov model. And those are also fairly straightforward because we have a very well-developed theory of quantum Markov processes. So, there's a way to more or less translate the classical Markov process to a quantum Markov process if you want.
Later you find out about the beta guy. So I think you need to focus.
You see the kids.
Sorry, that's you through here. Then let me switch off. No, I can switch off the mic here. The speaker.
All right.
Yeah, sorry.
That's okay. So then we'll get chats. So to take a step back, is the idea that we're hoping that by reformulating the machine learning process onto a quantum computer, that there'll be some kind of exponential speed up for some
That's the whole
process. Yeah.
That's the hope.
Okay.
That's the hope. Like all of quantum computing. If you don't have an exponential speed up, or at least a strong polynomial speed up, it will take a long time before you beat a big classical computer or the CHPC. Maybe a little bit less time for the CHPC. But a long time before you beat the fastest supercomputer that we have at the moment. Yeah?
Super. Thank you.
Yeah. Okay. So combining now the things. Yeah. This is I showed you this slide last time. Yeah. We can have classical and quantum algorithm and classical and quantum data. Yeah. What I will speak about today is classical data and quantum algorithm. Yeah. There are other options as well. Yeah. And again, what is the problem? Yeah.
Sorry, go ahead.
So if you have a standard machine learning algorithm, yeah, you are given some data sets, you do your ChatGPT thing, yeah, and you give a prediction of something. Yeah. The quantum algorithm needs to do the same. Yeah, you want a data set, use the same classical data set, and you want hopefully the same or better prediction. Yeah. The difference is that now, if you deal with quantum systems, we need to do what's in the dotted box. Yeah, we need to prepare the state of the wave function. Yeah, we can only do unitary evolution, and we need to measure. Yeah, so that means that around the algorithmic part, there is an encoding part, yeah, because you need to transform the classical data into quantum data, yeah, and there are various strategies for that. Then you apply your quantum algorithm, yeah, and then you need to measure it, yeah, and out of the measurement, yeah, which is intrinsically probabilistic, yeah, you need to do your prediction, yeah? And hopefully they're the same, yeah. So this is a general setup. Now come the parentheses for you. Yeah, probably the most basic algorithm, yeah, is this famous Deutsch algorithm. Yeah, and it's a typical example of an oracle kind of based algorithm. Yeah, because if you look, I think I cut and paste this from Wikipedia. Yeah, the definition of oracle more or less. Yeah. it's just some kind of black box, yeah, so that you don't really care what's in the black box, but something comes out, yeah, and mainly used to prove something, yeah, it's not really, yeah, but to show it in action, yeah, I want to give you now something that is really very nice and not so well known. You know, usually those of you that you are more experienced in quantum computing know that the standard version of the Deutsch algorithm is for 2 qubits, yeah? But you can do it with 1 qubit as well, yeah. So that, for instance, if you have imagine you have your oracle is some black box UF because it's a unitary operation and that describes some function from 1 bit to another bit, yeah. So you can define, for instance, a phase oracle, something that is defined like that. If x is 0, 1, u of f is -1 times f of x applied to x, yeah. So that is f of x is 0, nothing changes. F of x is 1, you multiply by -1. So you have a phase change. Yeah? And the Deutsch algorithm works like that. And you know, it's the famous algorithm that allows you to describe, to find out whether a 1-bit function is balanced or constant. Yeah, balance means let's say constant, of course, constants, yeah, and balance f of 0 is 1 and f of 1 is 0. Yeah? So that's the 0 and 1s on the right hand side appear with equal probabilities, so to say. Yeah? So this is how it works. Yeah? You prepare your qubit in state 0, you apply a Hadamard that creates the superposition, the blue thing here on the left, this thing there. Yeah. Then you apply your oracle, yeah. So the UF applied to we are here to the superposition, yeah. UF of course is linear, so you apply to 0, apply to 1, and the result, if you write it a little bit more compact, yeah, you can write it as plus minus state plus, which is 1 over square root of 2, 0 plus 1, or minus 1 over square root of 2, 1, 0 plus 1, yeah, and so on and so forth. So that when you measure it after the oracle, you push it again to a Hadamard, and the side 3 is the state in blue on the right. Yeah, it's either plus minus 0 or plus minus 1. Yeah, in one case the function is constant, in one case the function is balanced. Yeah? So that just with one measurement and with one oracle call, you can find out a global property of a function. Now, if you were to do it classically, you should evaluate f of 0 and f of 1. Yeah, if you do it quantum, just do a call of UF, and that's it. Yeah. So this is the basic idea. Yeah. So now, inspired by this, and I don't know why this stayed there. Can I remove that? I don't know. Sorry. No. Sometimes you try to be fancy and then it doesn't work. I might have painted on it, but there is nothing to delete. Sorry for the annotate. Sorry.
How when you annotate, you can delete. I was. Yeah.
Oh, okay, I don't know. Sorry, now there is that line there. I don't know. I messed it up. Yeah. Anyway, so a minimal quantum circuit, yeah, a quantum machine learning circuit. And you see, this is something that is also a while ago. Yeah, and Maria, who was a PhD student at the time, works now for Xanadu, that is a big quantum computing startup in Canada. Mark has his own startup in Canada, yeah, that is called Protein Cure, and tries to find proteins to sell to the pharmaceutical industry using machine learning on quantum computers. And I'm still professor. So I'm doing something wrong. Anyway. So just some notation, and I think in the next slide I will show you exactly how it works. Yeah? We have some data set, yeah, some data set D that has some values X and a label Y. Yeah, to make things simple, the label can be -1 and 1. Yeah, and that's simple. As a preview, yeah, we want to implement a classifier that is a simple distance measure classifier. Yeah? So that we want is a square distance between as a kind of a kernel for binary data. Yeah. So a distance-based classifier. This is what we will implement. Yeah? And the and the strategy is first step, as I told you before, we need to put the data into a quantum state. Yeah. So one way of doing it, yeah, is you take your data here, yeah, and you encode them in the amplitude of a state vector. Yeah. Of course, you need to make sure that the data normalize and so on and so forth. So this is one way of kind of amplitude encoding of classical data. Yeah? There are other ways, but let's stay there. Yeah. Then we want to prepare the state. Yeah. And that we do again the usual training set. Yeah, we prepare a state vector D that contains now the training values. Yeah, and we need to create this kind of funny superposition that contains the labels, the data, and your kind of ancilla vector of sorts. Yeah? If you have that, this is your classification state. Yeah, you see, that's why I said it's a little bit like the Deutsch algorithm, because you have just one Hadamard and two measurements essentially. Yeah. So in the first step, yeah, which is the application of the Hadamard, you create this kind of superposition between your data set and your qubit and the label vector. Yeah, the psi x plus x tilde plus xm, and x tilde plus is what the state that you obtain after the Hadamard. Yeah? Yeah, then you measure. Yeah, you measure in step B, and you get some success probability that has that you can easily do the math. That is usually around 1/2, yeah, more or less. Yeah, not surprising, yeah, because you have a Hadamard, it goes. Yeah. Yeah, and then you do a step of kind of conditional measurement in C. Yeah, and if you do it properly, the probability to measure a certain level is given exactly by that kernel that I showed you at the beginning. Yeah. And this is the same slide as before. Yeah. So this is exactly the same. So that with a very simple circuit, you can classify data that have a binary level. Yeah. And we show that it works, yeah, for a very simple data set. Yeah, we used this traditional iris flower data set that has been up for a long time. Yeah, where for different types of irises, you have the data for the sepal length and width and petal length and width and so on and so forth. Yeah. So, like in classical machine learning, you need to pre-process your data a little bit. Yeah. You start with your raw data, then you standardize them, so make sure that it's zero mean and univariance, and then you normalize them as well. Yeah, so that you operate just with the normalized data. Yeah, and here's the very simple data set. Just a couple of points. Yeah, because we had only a couple of qubits. Yeah, so that's the number 33 and 85 in the data set. Yeah, so the points that are marked in the circle. Yeah, and these are down here are the points that we want to classify. Yeah, we want to give the label. So these x0 and x1, we know the label. Yeah, we use them to teach the machine learning algorithm, and then we want to find the label of these 2 points. Yeah. That are the points here in the red part of the thing. Okay, so you need to input the vectors, these numbers into the encode them into the amplitude of your qubits, which is done here. Yeah. And this is the important slide that I want to show you. Yeah. Important because you see, this part of the algorithm is just a classification. Yeah? It's just one gate. All the rest is the encoding of the classical data in the state vector. Yeah. So it's way more complicated to input the data than to do the classification. And that is a typical problem of quantum machine learning. Yeah. That even if the classification is fast, if this takes much longer than a classical computer would do, you've lost before you start. Yeah. So this is the problem. Yeah. In fact, it's even worse because these dotted boxes. Sorry, that comes later. Yeah. So I think I don't need to show you. So there are various steps to get the data into your qubit, and then you eventually can start with the classification. Yeah? And in fact, it's even worse because you remember the dotted square boxes, each of them are a box like that. Yeah. So it's even worse than what I showed you before. Yeah. But fact is that if you do a little bit of statistics, in this case it was 8,000 odd runs, you can classify fairly appropriately, yeah, the two unknown points and give them the right level. Yeah. So more or less, you see, if you compare the simulation with the theoretical values, it's very nice. The experimental on a quantum computer that we had at that time, yeah, it's also decent. Yeah, so it works. Yeah. Okay. Now, so okay, I've spoken much longer than I thought. Okay, now we jump a little bit to more modern things. Yeah? Variational circuits as machine learning models. Yeah? The principle, I mentioned it already last time, it is very simple. Yeah, because we have these noisy quantum computers, what people make use a lot are hybrid approaches, where you do have a piece on a quantum computer and a piece on the classical computer, and hope to get some advantage out of it. Yeah? So the basic idea, you have here your quantum computer that where you measure something, yeah. Then you push the measurement through a classical optimization routine where you try to minimize some cost function that depends on some parameter that is part of your circuit, and then you feed it back into the scheme and so on and so forth until you're happy with your results. Yeah? Probably the most famous of these variational algorithms are these variational quantum eigensolvers, yeah, which is very close to the heart of physicists because we want just to minimize some Hamiltonian, yeah, and you find the cost function as the expectation value of that Hamiltonian with some parameter, yeah, and typically, for instance, you would have a Hamiltonian that is sum of some other Hamiltonians, yeah, typically written, expanded, and kind of Pauli operator Hamiltonian as an example, yeah, and so that the expectation value can be then written in this form, and the cost function could be a sum of local kind of expectation values. Yeah? So the strategy is then you do your averages for every piece of the Hamiltonian, you put them together, and you calculate your expectation value. For instance, just to show you the principle. Yeah? This is now very, very simple. Yeah? You start in 0 and you want to measure sigma z. And of course, the expectation value you can calculate in the head. Yeah? But now you put in something in between, and of course it changes. Yeah? But so that the next stage is, of course, that you introduce unitary operators that depend on some parameter, yeah? And you still want to measure in sigma z, and you want to optimize it maybe to some value, yeah? So that you can do the strategy that I mentioned before. Okay, this is the same. So here's a very simple example. You could define your cost function, like something like that, yeah, and see how it acts on the qubit. And for instance, for this kind of simple one qubit circuit where you have a combination of a fixed rotation with a general rotation, and then you measure in Z, yeah, you can simply see if you start. Sorry, my finger is here. Yeah, you start with here. R of X maps the points here on the block sphere. Then you do the rotation. Then you measure sigma Z, and you see more or less where you are, and you can then define whether it's more 1 or whether it's more -1. Yeah. So this will be the general strategy. Yeah. Now, how do you train this variational quantum models? Yeah? You can do it like you do in classical machine learning. You can do some kind of automatic differentiation that has a quantum part and a classical part. Yeah? But you can also do more fancy things. Yeah? You can use this kind of parameter shift rules where you take the derivative of the circuit. Yeah? You look at the circuit if the parameter mu plus s and mu minus s, and you calculate the expectation value and calculate the difference. Yeah? You can do this kind of things. Yeah? So that it's also fairly, once you know that it works, it's fairly straightforward. Yeah. Now, within these variational models, there are various classes. Yeah, we can have, for instance, deterministic models, for instance, for supervised learning. And the typical structure is the following one. You have always two. So the initial condition is always 0. Yeah, you start with the vector 0, 0, 0. Yeah, then you have a block S, which is the data embedding block. So you need to embed your data in something. Yeah, then you have your circuit that is parameterized, and you measure, you average, and you calculate some expectation value of some model. Yeah? And if you want, you can introduce some feedback loops of sorts. Yeah? So this would be a very simple variation circuit for machine learning. Yeah? If you have a variant where for instance, this average procedure is missing, yeah, then what you obtain after the measurement is just some kind of conditional probability distribution. Yeah? So that it's essentially the same circuit, but instead of calculating an expectation value, you obtain some distribution. Yeah? A very simple example are these Born machines, yeah, which is again a kind of a variant of this here. Yeah, you see this block is missing, yeah? And in this case, you just obtain a probability distribution. So you can just use this kind of algorithms to samples. Yeah, that's what they try to achieve supremacy. That's essentially what they. Yeah. Okay, so but what does all of this have to do with neural networks? Yeah, because so far we haven't seen a structure like that anywhere. Yeah? The idea is that you have, like in a neural network, yeah, you have various layers of gates. Yeah, and you can have okay, the green is always the initial condition, the embedding of the data, and then you can have various layers. Yeah, some can be fixed without any parameter, and some might have a parameter that you want to optimize. Yeah? And this is essentially what people call the quantum neural network. Yeah, so you have gates with a parameter that you can train. Yeah, with the procedure of the feedback that we mentioned before. And now you see where the linearity comes in when you essentially when you measure. Yeah, that's the point where things get a little bit interesting. Yeah, so this is why these things are called quantum neural networks. Yeah? Okay, so now I'm not okay. I think I was faster than I thought. I was slower than I thought at the beginning and faster now. Now let's go to something more interesting. Yeah, convolutional neural networks. Yeah, convolutional neural networks have been around for some time in classical machine learning, and the idea is for instance the following: you have some image and you want to classify it. Yeah. And how you do it, you have various layers that represent some kind of convolution. Yeah. Then you have layers where you essentially including some feature match, you reduce the dimensionality of the system. Then you do again the same trick of convolution. Then you reduce again the dimensionality of the system, which is called pooling. And then eventually, when everything is then fully connected, yeah, you can say it's a hexagon. Yeah. So how do you do it quantum? Yeah. And this was proposed maybe 4 or 5 years ago, yeah, by this trio, yeah. And the idea is essentially the same. Yeah. You have also various layers in our variational circuit, if you want. Yeah. Some represent the convolution, some represent the pooling, yeah, and there is some kind of measurement that is fed forward to the next convolution layer, yeah, and so on and so forth, yeah, until then you measure and decide whether your photo is a cat or a dog, yeah. But if you look at this, you can immediately see that there's a kind of structure in the system, and there are probably lots of parameters, yeah, that you need to optimize, yeah, which is probably not so good. So that there is need to look at doing it maybe in a little bit more efficient way, yeah. And this is what what we did. Oops, sorry, now I have to go back.
But I get the issue of just about to look, I completely with all of you guys. So I must know all your test needs so that when I'm suggesting things, I'm not suggesting that I'm not going to accommodate others.
Very simply, we wanted to do a quantum version of
I don't know why people have been sent already, so that I can come up with
and see if we can classify music.
and then choose. Because I'm rating on the face, I'm also rating on the 4th of September. So I want that's why I'm saying like interesting because we can choose to pass this one and then we take it somewhere around to the imagine now we were taking it to the end of
and we did it with this
I can't remember. Must be maybe a week before the 4th or after the 4th, you understand? So that's why I want to take all the things so that we can enforce the things. I don't know why you guys are not doing it.
Okay. And again, if you remember the previous slide, you recognize that there were the convolutional level layers, the pooling layers, and so on and so forth. Yeah. And
Is that?
okay, I will explain this just now. Yeah. So, what was the problem that I tried to address? Yeah. One is that we try to find a kind of optimal quantum circuit. Yeah. So that for a given kind of feature map, essentially you find the architecture, the circuit architecture that has the least possible number of parameters. Now, because the more parameters they have, the more wild it can get. Yeah, and this is what Matt did really very nicely. Yeah, because he identified, essentially mapped it on a kind of a graph hierarchy of graph problems. Yeah, and you can see, for instance, here that you start with kind of at the very bottom layer, so to say. Yeah, with some sequences of 2-qubit gates. Yeah, that you then want to put together and optimize. Yeah? And then you can introduce these graphs that allow you to describe the convolution. Yeah? For instance, here you have a convolution on you see convolution in this way. You can do the convolution in this other way, or there are different levels of doing the convolution or the pooling. Yeah? Blue is always the convolution, red is the pooling. Yeah, you can do it at different levels. You can here you can do it at level 2, yeah, or a more complicated level, or even by clustering 4 and so on and so forth. Yeah. So this was the strategy, and you find the optimal one by applying some kind of evolutionary optimization algorithm of sorts. Yeah. And to show that it works, yeah, we applied it to the same problem that the original proposal of this quantum convolutional neural network studied, which was essentially to find the ground state of some easy Hamiltonian of this form. Yeah. And in the original paper, they had, I think, some 1,300 of parameters with the algorithm and the architecture search that that Matt proposed. He managed to reduce it to 11. Yeah. And if you look at the phase diagram that you managed to distill out of that, it looks exactly like it should. Yeah. So it's really very, very, very nice. Yeah. So you can really do problems of this kind with this kind of quantum. And this is a problem with 15 spins. So it was not too bad. Yeah. And Matt went to the whole trouble to prepare a proper Python package, yeah, that he called hierarchical. Yeah, that and it's in GitHub, so everybody can. You see, a quantum circuit builder that simplifies circuit design. So it's not just limited to this example. That's a very generic package now that you can use for almost anything. You can even do Grover with it. Yeah. And in fact, that they're adding a tutorial on Grover, I think, these days. Yeah. Yeah. So just to test it on some other setup. Yeah. And because we're in South Africa, we have the SKA, so there is lots of pulsar data around, yeah, although they're stored in the US. I don't know. And it's a database that is with 17,000 data. Yeah. So it's not big data, but it's also not small data. Yeah? So way bigger than the 2 data points of our Hadamard classifier. Yeah? So it's already a big step forward. Yeah. And Donovan, this other PhD student, and he gave me these pictures this morning, yeah, because everything takes longer than you plan. Use the package that Matt produced, and which is again, you see some convolutional neural network with the usual convolution pooling and so on and so forth stages, layers, and compared it to a support vector machine. Yeah, so this is just the graphical representation of a support vector machine with some simple feature maps of sorts. And he applied it to this data set. Yeah. And again, so the color coding is pink is convolutional, green is support vector machine. Yeah. And he analyzed the data, and the best thing would be is to give a look at this what's it called? The confusion matrix. You see the non-pulsar pulsar, non-pulsar pulsar on the y-axis and on the x-axis. So that, for instance, the non-pulsar data are data that are identified as non-pulsar and are really truly non-pulsar. Yeah? The pulsar, non-pulsar data are the data that you classify as pulsar, but unfortunately are not. Yeah, and so on and so forth. Yeah, and the pulsar data are the data that a pulsar and a real pulsar. Yeah? And this in green was the support vector machine, and this is the feature map, the feature vector where yellow is towards 1. I think he forgot to add this line underneath, but it will come. Yeah, and underneath here are the data for the convolutional neural network. You see that they're fairly comparable. Yeah, maybe the convolutional. The support vector machine maybe does a little bit better as 31 right one compared to 28. But the big difference is that, and here are some other 8 features that quantify how good it is. And so when it's one is that there's the classification, and the others are some of the off-diagonal components and so on and so forth. But the point is that although the support vector machine looks a little bit better, it's way slower than the convolutional neural network. Yeah, so that if one day you have really bigger data sets, the way to go is the quantum convolutional way, because if you compare the evaluation times on on a quantum computer, it's way faster, yeah? And it has also a very limited number of parameters and so on and so forth. Yeah. So this is the last thing that that we did fresh from this morning. Yeah. So I couldn't have shown it to you 2 weeks ago because we had similar plots, but it turned out that they were wrong. Yeah, because there's something went wrong somewhere. Yeah? But anyway, we fixed it. Yeah. So this was essentially a very short overview of quantum machine learning from a personal perspective. Yeah, because in the early days we were very proud to have developed this this Hadamard classifier, yeah? Which I still believe it's a very useful example. And in fact, in some some of these tutorials, I don't know, Penny Lane, it's sometimes used as a tutorial, so you can do it. And if you use them, yeah, it's it's a few lines of code. It's not so difficult. And then I showed you the basic idea of variational quantum circuits and how you can use it to what is probably more state-of-the-art quantum machine learning at the moment. And yeah, and that's it. And if you really like it, you can read this. And you can speak Japanese, you can read in Japanese as well. And soon in Korean. Yeah. Very good. Yeah, so thank you very much.
Okay, super. I'm gonna hold on to the laptop in case there are questions from the audience that are online. But first, let me ask if there are questions from folks in the university. Yes, please go ahead.
So is the reason the convolutional one is much faster than support vector machine because you have to work out the whole kernel matrix first for the data points.
Yes.
So it's just more overhead.
Probably yes.
Okay.
Yes. And because of this optimization of the circuit, you really manage to do it with very few parameters and it of course very well. You know? But if you want all the details, you have to invite Matt.
Yeah.
Super.
Actually, I was going to ask a relatively technical thing on for the support vector.
Yeah.
It seemed like it had a lot of false positives relative to how many true.
Yes, that's possible. Let's go back. Sorry,
The top right one, he said it was thinks true, but it's
this one here.
yeah.
Yeah.
It seems to have a high rate of false positives relative to the.
Yes, but has more true positives. So it's I don't know. That's how I didn't
prejudice, right?
I didn't think too much about it because I saw this plot this morning. Yeah?
Okay.
But that's true. Yeah. So it's difficult to gauge, but you're mainly interested in the true positives. Yeah.
Yeah.
And those are in both cases okay. And you're also interested in the false. False. No, in the in the false negatives. Yeah. Because those are the ones that you need to go back and check and blah blah blah. Yeah. So the outcome, I mean, is probably comparable. I would say. Yeah. Yeah. I don't know. I'm not a pulsar physicist. I can't tell you how desperate the astrophysicists get if that number is 14 instead of 2. I don't know. But if you just naively, at least the non-pulsar, both of them are more or less okay. Yeah, and the true positives as well. Plus minus 2, they're more or less in the error bars. Yeah? And you see also you are in the first quadrant, the error bar is quite big. Yeah?
Right.
Yeah, so that you're almost there. Yeah, and at the end of the day, they probably do it with some classical machine learning. And
yeah,
it takes 3 seconds. Right? Yeah, but it just in the hope that one day we can get bigger data. Yeah, but you know, if you think that we started with 2 data points and now it's 17,000, that's already not too bad.
Do you know what encoding he used for the rotational?
Yes. We hope before the end of the month to have the paper in the archive. That's the hope. Yep.
We had a question online from Laurent asking, in the QCNN pulsar classification, was it performed on real hardware or without noise? And then Donovan responded,
Oh,
Yeah.
that's perfect.
Yeah. the runs were all on simulators. I tried performing it on real devices, but it tends to take too long. Noise would obviously be a big problem for such a long circuit.
But he did simulations with noise.
Mm. Good. Any? Yes, please.
Well, in terms of parameters, do you have a way to judge a priori how many you would need with an algorithm like this, or what affects how many you need?
I don't know. You know, when we compared it with the original convolutional neural network, they had more than 1,000. Yeah, and it turns out you need a dozen or so. Yeah,
And that was achieved by trial and error, or playing
No.
around with it.
No. That was achieved by systematic genetic algorithms and so on and so
Okay.
forth. Yeah. So there is a little bit of serious compression in the number of parameters possible. Yeah. I don't have our rule. Yeah. You know, maybe there is, but I don't know. Yeah.
Okay.
No, that's why, you know, we started essentially by trying to reproduce and do better what others have proposed. Yeah? And now we start using it with other data that to see what we can what we can learn. Yeah. And
So if we were to open up for more parameters, would that noticeably change your outcome?
no, probably not, because you know you just want to optimize the circuit. So you don't want to change the outcome. You want to make it leaner. Yeah. Yeah.
Good. Last questions from the audience, virtual or in person?
What is the coffee?
Yeah, where's the coffee? All right, so let's thank our speaker for giving us talk today. And for the two, not in a row, for the two, thank you so much.
No, anytime. There's more on stock.
You will call.
Can I stop the recording?